Today we're going to talk about confidence intervals for one sample means. Now that we know how to create confidence intervals about proportions, it'd be nice to be able to do the same for means. Just as we did before, we will base our confidence interval on the sampling distribution model. The central limit theorem told us that the sampling distribution model for means is normal with mean mu and standard deviation sigma over radical n. All we need is a random sample of quantitative data and the true population standard deviation sigma. Well, that's a problem. Proportions have a link between the proportion value and the standard deviation of the sample proportion. This is not the case with means. Knowing the sample mean tells us nothing about the standard deviation. We'll do the best we can, estimate the population parameter sigma with the sample statistic s. Our resulting standard error is s over radical n. We now have extra variation in our standard error from s, the sample standard deviation. We need to allow for the extra variation so that it does not mess up with our margin of error, especially for a small sample. And the shape of the sampling model changes. The model is no longer normal. So what is the sampling model? William S. Gossett, employee of Guinness Brewery in Dublin, Ireland, worked long and hard to find out what the sampling model was. The sampling model that Gossett found has been known as Student's T. The Student's T models form a whole family of related distributions that depend on a parameter known as degrees of freedom. We often denote degrees of freedom as df, and the model as T sub df. When the conditions are met, the standardized sample mean, T equals x bar minus mu over the standard error, follows the Student's T model with n minus 1 degrees of freedom. We estimate the standard error with s over radical n. When Gossett corrected the model for the extra uncertainty, the margin of error got bigger. Your confidence intervals will be just a bit wider than they were with the normal model. By using the T model, you compensated for the extra variability in precisely the right way. Students' T models are unimodal, symmetric, and bell-shaped, just like the normal. But T models with only a few degrees of freedom have much fatter tails than the normal. So we have a normal model, which is the dotted line, and we have the solid curve, which is the T model with 2 degrees of freedom. As the degrees of freedom increase, the T models look more and more like the normal. In fact, the T model with infinite degrees of freedom is exactly normal. The Student's T model is different for each value of degree of freedom. Because of this, statistics books usually have one table of T model critical values for selected confidence intervals. Gossett found the T model by simulation. Years later, when Sir Ronald A. Fisher showed mathematically that Gossett was right, he needed to make some assumptions to make the proof work. We will use these assumptions when working with Student's T. Randomization. The data arise from a random sample or suitably randomized experiment. Randomly sampled data, particularly from an SRS, are ideal. When a sample is drawn without replacement, the sample should be no more than 10% of the population. We can never be certain that the data are from a population that follows a normal model, but we can check the nearly normal condition. Pictures tell us far more about our data set than a list of the data ever could. The only reasonable way to check the nearly normal condition is with graphs of the data. Make a histogram of the data and verify that its distribution is unimodal and symmetric with no outliers. You may also want to make a normal probability plot to see if it's reasonably straight. The smaller the sample sizes, the more closely the data should follow a normal model. For moderate sample sizes, the T works well as long as the data are unimodal and reasonably symmetric. For larger sample sizes, the T methods are safe to use even if the data is skewed. When the conditions are met, we are ready to find the confidence interval for the population mean mu. Confidence interval is x bar plus or minus T times the standard error, where the standard error of the mean is s over radical n. The critical value T star depends on the particular confidence level C that you specify and on the number of degrees of freedom, n minus 1, which we get from the sample size. Take an example. A professor was curious about her students' grade point averages. She took a random sample of 15 students and found a mean GPA of 3.01 with a standard deviation of 0.534. Find the 99% confidence interval for the mean GPA of the professor's students. So step 1, we're going to check our assumptions and conditions. It tells us that we have a simple random sample. Population size is greater than 10 times 15. We can safely assume that. Sigma is unknown, so we're going to have to use T star. If they had given us sigma, we would use Z. And since we don't know anything about the data, we will have to assume a normal distribution. Step 2 is calculate the confidence interval. There's our formula. X bar plus or minus T star times S over the radical n. Plugging in our numbers, 3.01 is our X bar. Our T star is 2.977. That's what you get for 99% confidence with 14 as a degree of freedom. The degree of freedom is the sample size minus 1. S is 0.534, and then N is 15. So plugging this in, we get 2.6 to 3.42. So step 3 is our conclusion. We are 99% confident that the true population mean GPA of the professor's students is between 2.6 and 3.42. Our next example, the amount in ounces of juice in 8 randomly selected juice bottles are the following. Construct a 98% confidence interval for the mean amount of juice in all such bottles. Step 1, check our assumptions. Simple random sample is stated. Population size is greater than 10 times 8. We can safely state that. Sigma is unknown, so we'll use T star. Next, we'll have to determine if we have a normal distribution. Since we have our data, I've done a normal probability plot. Based on this normal probability plot and its linearity, we have an approximately normal distribution. Step 2, calculate the confidence interval. Here's our formula, plugging in our numbers. We got those from 1VAR stats on our calculator. So, sample mean is 15.6875. Our T star is 2.998. We got that from a 98% confidence interval with degree of freedom equaling 7. Our standard error is 0.405 divided by the square root of 8. We get 15.258 to 16.117. So our conclusion is we are 98% confident that the true population mean amount of juice is between 15.258 and 16.117 ounces. Remember that interpretation of your confidence interval is key. What not to say. 90% of all vehicles on Alpha Road drive at a speed between 29.5 and 32.5 miles per hour. The confidence interval is about the mean, not the individual values. We are 90% confident that a randomly selected vehicle will have a speed between 29.5 and 32.5. Again, the confidence interval is about the mean, not the individual values. The mean speed of the vehicles is 31 miles per hour 90% of the time. The true mean does not vary. It's the confidence interval that would be different had we gotten a different sample. 90% of all samples will have mean speeds between 29.5 and 32.5 miles per hour. The interval we calculate does not set a standard for every other interval. It is no more or less likely to be correct than any other interval. Choosing your sample size. In general, the sample size needed to produce a confidence interval with a given margin of error at a given confidence level is the following. N equals Z star times S over margin of error, whole thing squared, where Z star is the critical value for your confidence level. Now you'll notice, since I don't know my population standard deviation, typically we would have used T. Unfortunately, T needs sample size to determine what to use because the degree of freedom is based on the sample size. So, to be on the conservative side, what we're going to do is we're going to pick Z. So, make sure you round up your sample size that you obtain. An example. A government report on standard of living says that family income nationwide are skewed to the right and believes that the standard deviation to be 10,000. How many families must we survey to have a 90% confidence of estimating the mean local family income to within $2,000? So here's our formula. What we're going to do is we're going to plug in 1.645 for z because we're doing a 90% confidence. Sample standard deviation is 10,000 and our margin of error is 2,000. We're going to get 67.65, and rounding up, we get a sample size of 68.